Imagine you are strapped into a seat. The door behind you seals shut. You hear it lock. And you know with absolute certainty that you will never open that door again. Not in a year, not in 10 years, not ever. The people waving at you through the window, your mother, your best friend, the person you love, you will never touch them again. You will never smell rain. You will never feel grass under your feet. You will spend the next 4 decades sealed inside a metal cylinder, hurtling through a darkness so complete, so total, that the human brain was never built to process it. And here's the part that will keep you up at night. That is not the terrifying part. The terrifying part comes at the end of this video. And when I tell you what it is, I promise you, you will never look at the night sky the same way again. Let us rewind. Because before we get to what happens at the end of that journey, we need to understand what it would actually take to begin it. There is a star system sitting in the southern sky right now. You can see it with your naked eye if you were in the southern hemisphere. It looks peaceful. It looks close as stars go. It is called Alpha Centauri, and it is our nearest stellar neighbor, 4.24 light years away. That number sounds small. It is not. Light travels at 186,000 miles per second. It is the fastest thing that exists in the known universe. And even at that speed, light takes 4 years and 3 months to cross that gap. 4 years just for light. Now here's where it gets uncomfortable. The fastest spacecraft humanity has ever built is the Parker Solar Probe. At its absolute peak, screaming around the sun, it hits roughly 430,000 miles per hour. That sounds extraordinary. At that speed, you could get from New York to Los Angeles in 6 seconds. But if you pointed the Parker Solar Probe directly at Alpha Centauri today, it would arrive in approximately 6,700 years. The entire span of recorded human civilization is only 5,000 years. Our fastest machine would not even get close within one human historical era. So if we are ever going to reach that star, we cannot use what we have now. We need something fundamentally different. And scientists have ideas. They've had ideas for decades. Nuclear pulse propulsion, where you detonate nuclear bombs behind the ship and ride the shockwaves. Fusion engines that mimic the power of the sun itself. Antimatter drives that convert mass directly into pure energy with 100% efficiency. Laser-pushed light sails that could theoretically be accelerated to 20% the speed of light, with a ground-based laser array powerful enough to illuminate a small city. Each of these ideas has problems, serious ones. Antimatter sounds perfect until you realize we have produced less than 20 billionths of a gram of it in all of human history. At current production rates, accumulating enough to fuel an interstellar ship would take longer than the age of the universe. Nuclear pulse propulsion works on paper, but requires detonating thousands of nuclear weapons in space, which is both politically impossible and catastrophically dangerous. Fusion is theoretically clean and efficient, but after 70 years and billions of dollars of research, we still cannot make it produce more energy than we put in. The most realistic near-term proposal is a project called Breakthrough Starshot. The concept is to build a massive laser array, something on the order of 100 gigawatts, which is the output of roughly 100 large power plants, and use it to push a tiny spacecraft the size of a microchip to 20% the speed of light. At that speed, it would reach Alpha Centauri in about 20 years. No crew, no return. Just a few cameras, a basic sensor, and a faint radio signal beaming images back across 4 light years of empty space. That is the best idea we have right now for reaching another star, a chip. But what about sending people?
For that, the math gets brutal. Let us say, generously, that one day we develop a propulsion system capable of pushing a crewed spacecraft to 10% the speed of light. That is still 40 times faster than anything we have ever built. But let us say we get there. At 10% light speed, the journey to Alpha Centauri takes about 42 years, one way. You launch at 30, you arrive at 72, if you arrive at all. Now think about what 42 years actually means inside a spacecraft. You cannot open a window. There is no outside. There is no ground. There is no horizon. There is no weather. There's no night and day unless you program the lights to simulate it. You will breathe recycled air every single minute of every single day for 4 decades. You will drink water that was processed from your own waste, from the sweat of your crewmates, from the moisture of the air itself. The food will be grown in hydroponic chambers under artificial lights, and after a few years you will have memorized every meal by heart. You will exercise for hours daily because without artificial gravity, your bones and muscles begin to waste away. The only practical way to create artificial gravity is to spin the entire ship, and the rotation radius needs to be at least 100 meters for the forces not to make you nauseous every time you walk across a room. There will be around 50 to 100 people with you. You will know all of them within weeks. By year 10, you will know which ones breathe too loudly, which ones laugh at the wrong moments, which ones leave things in the wrong place. And there's nowhere to go. No separate apartment to walk to, no coffee shop to sit in alone, no park to clear your head. You are locked in permanently with the same small group of humans in the same corridors under the same artificial light until you are old. Studies from Antarctic research stations and submarine deployments, which involve isolation periods of 6 to 12 months, show consistent patterns. First comes excitement, then routine, then creeping irritation, then conflict, then either adaptation or breakdown. Now multiply that by 40. And then there's the radiation. In space, beyond the protection of Earth's magnetic field, you are exposed to cosmic rays constantly. High-energy particles fired out by dying stars and black holes across the galaxy. They punch through almost anything. They damage DNA. Over 42 years, the cumulative dose your crew would absorb is far beyond what medical guidelines on Earth consider safe. Cancer rates would be elevated. Some crew members would develop tumors years into the journey. The spacecraft hull provides some protection, but not enough, not nearly enough. And the void itself is not actually empty. At 10% the speed of light, a grain of sand has the kinetic energy of several kilograms of TNT. A pebble hits with the force of a small nuclear weapon. The ship needs a forward shield thick enough to absorb impacts, which adds mass, which requires more thrust, which requires more fuel, which adds more mass. It's a cycle with no clean solution. And communication with Earth, at the halfway point, you're roughly 2 light years out. A message takes 2 years to arrive. A reply takes 2 more years to return. You send a question and wait 4 years for an answer. By the time it arrives, the person who answered might have moved, retired, or died. Your children on Earth will have grown up entirely without you. By the time you reach Alpha Centauri, Earth will have changed so completely that the world you left will barely be recognizable in the history files. You will be more alone than any human being has ever been in the history of our species.
Now, here's the part I promised you at the beginning. Here is the terrifying thing that has nothing to do with radiation or loneliness or broken life support systems. You get there. 42 years. You made it. You are in orbit around Proxima Centauri b, the rocky, Earth-sized world that sits in what might be the habitable zone of our nearest stellar neighbor. Everything the mission was built for, everything you sacrificed, right there through the viewport. And then you start receiving a signal, not from the planet below, from behind you, from the direction of Earth. It is a mission update, and in it, Earth informs you that in the 15 years after your launch, engineers finally cracked the propulsion problem. A second ship was built, a faster one. It launched 10 years after you did, traveling at 30% the speed of light instead of 10. It will arrive at Alpha Centauri in 4 years. You spent 42 years traveling to a destination that a faster ship, built using lessons your mission helped teach, will reach in 14. The people on that second ship will be in their 40s when they arrive, healthy, young, ready to begin. You will be in your 70s, having spent your entire adult life in a metal corridor. And you will watch them land. You will watch them build. You will watch everything you sacrificed your life to achieve get done by people who came after you and passed you along the way. Astronauts and mission planners call it the weight calculation, the question of whether it is better to launch now with the best technology available or wait until technology improves. Because if you always wait, nobody ever goes. But if you go too early, you condemn a crew to a journey that history will render obsolete before they even arrive. There is no clean answer. There never will be. But here's what I want you to sit with. Those people on the first ship, the ones who launched knowing the risks, knowing they might never see Earth again, knowing they might spend 4 decades crossing a void, only to arrive old and tired at a destination that might be barren, hostile, or utterly inhospitable. Those people made the second mission possible. Their data, their sacrifice, their proof that it could be done at all, that is what convinced Earth to build the faster ship. They were not failures. They were the reason it worked. The journey to Alpha Centauri is terrifying, not just because of the distance or the danger or the darkness. It is terrifying because it demands something that almost no human being ever has to actually give. Everything. Your entire life spent in a direction you cannot turn back from, toward a destination you cannot be certain of, for a species that may or may not remember you by the time you arrive. And yet, someday, someone will go. They will look at that faint point of light in the southern sky, 4.24 light years away, 25 trillion miles of absolutely nothing, and they will strap in, and they will launch. Because that is what we do. We push, we go, we find out. The nearest star is right there, and we are already dreaming about how to reach it. If this journey moved you in any way, share it with someone who still looks up at the night sky and wonders, because those are exactly the people who need to see this. Good night.